Hey guys, so we are on chapter 19, part 3. I'm on slide 22 of the new PowerPoint that's on the shared class files. So we're picking up, we've introduced delta G, and we can use delta G to determine whether reactions can be spontaneous or not. So I have another reaction here, it's the combustion of methane. If I have that reaction going and I want to calculate delta G, actually first of all I want to predict whether it's going to be spontaneous or not. Will this reaction be spontaneous? Well, basically I'm going to have to think about two things. First of all, I'm going to think about delta H. This reaction is a combustion reaction. If it's a combustion reaction, I know that combustion reactions always give off a lot of heat. That's why we use them as a fuel source, is because they're exothermic. So if it's exothermic, that's a good sign that the reaction will probably be spontaneous. But if I look at the number of gaseous molecules, I'd see them starting with 3 gaseous molecules on the left, and I only have 1 gaseous molecule on the right. So in this case, the entropy is probably going to decrease, which is bad. So I kind of have a case here where if I look at enthalpy, I might think, hey, this is going to be spontaneous. If I look at entropy, I'd say, oh no, this definitely won't be spontaneous. How will I know which one it's going to be? Well, this is where I need to calculate my delta G value, okay? Because the entropy and the enthalpy kind of give opposite indications of whether it's spontaneous or not. Neither one of them by themselves can tell me. I have to calculate delta G to know for sure whether it's going to be spontaneous or not. So, how would I do it? Well, easiest way probably is just looking in the appendix, get the delta G of the products, the delta G of the reactants, subtract them, gives me delta G of reaction. And this is going to be the delta G of reaction under standard conditions. Remember, whenever you have the not symbols, that always means standard conditions. So that would be if I had a container that had 1 mole, actually a gas, 1 atmosphere of partial pressure of CH4 in the container, 1 atmosphere of oxygen in the container, and 1 atmosphere of CO2 in the container, and then liquids don't matter really, so I just have to have some liquid in the container. But if I had 1 atmosphere of each of the gases, those are standard conditions. When I determine that the reaction, if delta G naught comes out to be negative, what that means is under those conditions, the reaction still wants to go right. So we're not talking about here having CH4 mixed with O2, put them in a container, close the lid. When I calculate delta G naught, that's not what we're calculating there. Okay? We're calculating if everything is present in the amounts that are controlled by standard conditions, then that's what delta G naught is. And if it's negative, then under those conditions, the reaction will move forward. Okay? If I want to calculate will the reaction go forward with just reactants and no products, that's not going to be standard conditions anymore. That's going to be just delta G without the not symbol. And we're going to get to that in a little bit. Okay? But it's important to understand, like with each of these things we're calculating, what's the context that applies. So, will a reaction have a negative delta G or not? On that reaction I said it's exothermic, which is good. It loses entropy, which is, the entropy decreases, which is bad. They're contraindicative of each other. So how do we know whether it's going to happen or not? Well, this chart kind of lays out, I mean, there's different ways to look at this, and I'm not going to spend too much time explaining it now because you need to read about it. But I know if I want to get a negative delta G value, the best delta H value I could have to give me a negative delta G, I would want delta H to be negative. If delta H is negative, that's going to give me a better chance of having a negative delta G. I want delta S to be positive. Because if I do some number here minus a positive, temperature is always positive in Kelvin, and delta S is positive, so if I do a number minus a positive, that's more likely to give me a negative delta G value. If delta S was negative, if I subtract a negative minus and negative, they change signs, I end up adding a positive number, that's going to be more likely to give me a positive delta G. That would be bad. So the ideal scenario for a spontaneous reaction is going to have a negative delta H and a positive delta S. If I have that combination, it doesn't matter how big the numbers are, it doesn't matter what the temperature is. A negative minus a positive will always give me a negative delta G. So on this chart, right here, if I have a negative delta H and a positive delta S, it's always the midpoint where delta G equals 0. If I'm below here, I have a spontaneous reaction. If I'm up there, I have a non-spontaneous reaction. So with a negative delta H and a positive delta S, this part of the graph is always in the spontaneous region. So under those conditions, it'll always be spontaneous regardless of the temperature. Okay? Now, what's the opposite of that? If I had a positive delta H, that's bad. If I have a negative delta S, that's bad. Positive minus a negative becomes positive plus positive. That's this one up here. Positive delta H, negative delta S. With that combination, I'm always in the non-spontaneous region. So with those two values, it doesn't matter what the temperature is, that reaction will never be spontaneous. Okay? But then I have the two possibilities. What I've done so far, they were both good, that put me down here. They were both bad, that put me up here. So now, what about if one's good, one's bad? That's going to be where temperature is the determining factor. Okay? So let's just say, what if both are positive? If delta H is positive and delta S is positive, under what conditions will it be spontaneous? Well, I kind of have to look at the values. Positive minus a positive, in order to get a negative answer, I would need this number to be bigger. If both values are positive, I need to be subtracting the larger value over here. How would I make this number get bigger? I would have to have a high temperature. So if delta H and delta S are both positive, having a high temperature is going to favor spontaneity. Basically what will happen is, above a certain threshold temperature, it'll become spontaneous. If I go below that temperature, this term will get too small, and this one will dominate, and it'll be non-spontaneous. So when they're both positive, I have to go above a certain temperature to make it be spontaneous. Now, what about the last possibility? If they're both negative, negative minus a negative. In that case, and again, minus a negative means I'm going to add a positive over here. The negative plus a positive, I need this value to be the dominant factor. How will I make this one be dominant? I need to shrink this one down. To shrink this one down, I'm going to want to have a low temperature to make this value smaller. So when both values, delta H and delta S, if they're both negative, then that reaction will be favored at low temperature. Okay? So I have a combination where it's always spontaneous, I have a combination where it's never spontaneous, I have a combination where it's spontaneous at high temperatures, and I have a combination where it's spontaneous at low temperatures. You need to be able to think your way through that on a given situation and answer a question. So that's what the next slide is. If I have a reaction where both delta H and delta S, if they're both positive, then under what conditions will the reaction be spontaneous? So delta H, delta S are both positive. So if I go back, if this is positive and this is positive, I need to subtract a bigger number than the positive number I started with. So in order for this term to be the dominant term, I need high temperature. So on the next slide, it says the second part of the equation, the T delta S, needs to be the dominant factor. It needs to outweigh the delta H, so that I'm doing a positive number minus a bigger positive number. That'll give me a negative answer. So that reaction will work if you do it at high temperature. So we have an actual reaction here. When we dig iron oxide out of the ground, and we need to reduce the iron, iron in nature is almost never found in its pure form. So we dig out iron ore, which is iron oxide or iron sulfide, and then we have to reduce it to get the metal iron. Okay? The delta G value here is a positive value under normal conditions. Under standard conditions, it's a positive value. That means it's not spontaneous. So we can't get this reaction to go under normal conditions. But we know if we calculate delta H and delta S for this reaction, they're both positive values, which is what we just talked about. So essentially what that means is that if we raise the temperature to a high enough value, then the reaction, as the temperature goes up, the delta G value is going to change. It's going to go down. And if we get it to go down far enough that it becomes negative, then the reaction is going to happen. So how do we do that? So there's my delta H and my delta S. I have those two values. So at what temperature would this reaction become favorable? How hot do I have to get this reaction to make it work? Okay, how am I going to solve that? Well, I'm kind of looking for the temperature where the delta G, it's positive normally, but I want it to become negative. And that crossover point where it goes from being non-spontaneous to spontaneous, that crossover point is when delta G equals 0. So I'm going to set up the equation, delta G equals delta H minus T delta S. I'm going to plug in a 0 for my delta G. And then I know what delta H is, that goes here. I know what delta S is, that goes here. And I solve for my temperature. And when I get that temperature, that's going to be the answer. That's going to be the temperature where it goes from being non-spontaneous to spontaneous. Now, the trick here, though, is, number one, the temperature needs to be in Kelvin. And when you solve for it, it will be in Kelvin. And then number two, we got to remember our units. Delta H is in kilojoules. Delta S is in joules. Now, since I'm plugging in a 0 for delta G, it doesn't matter this time whether I put them both in joules or in kilojoules, but they have to match each other. So put them in the same unit, plug them both in, plug in 0 for delta G, solve for T, and when you do that, actually have the answer for this one, you should get that the temperature is around 3,000. I think it's just under 3,000. Now, that means that in order to reduce iron, we would have to heat this reaction up to over 3,000 Kelvin, which is a really high temperature, to make it work. That's not really feasible. If we had to do that to get iron, it wouldn't be financially worth it for companies to do it because it's really hard to get a fire that hot. So what we do instead is we like to couple reactions together where we have this reaction under normal conditions has a positive delta G. If we combine it with another reaction that has a negative delta G, Hess's law says if we add them together, the two reactions, if we run them simultaneously in the same container, if we do that, then their delta G's should also combine. And if we combine their delta G's and get an overall negative delta G, then we can get both processes to work. So that's what's on the next slide. So instead of running the reaction at such a high temperature, we're going to combine it with another reaction. The combustion of carbon monoxide. If we burn carbon CO with O2 to make CO2, the delta G of the reaction, if we normally balance this equation, it'd be 2 to 1 to 2, and the delta G for that reaction would be negative 514. Now, when we combine them, we have to look at the stoichiometry and make sure everything matches up. Specifically, the electrons of the oxidation and reduction are going on. Again, that's a chapter 20 thing. But all in all, to balance this equation, we have to triple this one, so that's why we tripled that. We also have the iron oxide being reduced to iron reaction. We had to double that one. Again, it's just electronically trying to get the oxidation and reduction to match each other. Don't worry about that too much. But if I combine these two reactions, my overall reaction occurring is this. The iron oxide is getting reduced to iron, the carbon monoxide is being oxidized to CO2. One of them is a positive delta G, the other is a negative delta G, but when I combine them together, my overall delta G value is negative. That's what I need in order to make this reaction happen. In industry, when we get iron out of the ground and dig it out and want to purify it, this is the process that's done on a daily basis around the world. All right, video's getting long, so I'm going to cut this one off again and do one more for this chapter.